We're studying our IGCSE physics. Today we're doing magnetism 8. This is the eighth class on magnetism. And we'll be looking at everything related to the applications of inducing EMF, and also the applications of inducing applications of force due to current. Now these two things, that's what we'll do today. But before we start that, I want to revise a bit about induction, how EMF is induced. Now Anas, do you remember how is an EMF induced in a wire which has no battery? Do you remember anything about this? 1 point. First, let's start with Neha. Can you tell me what is the right hand rule?
Sir?
What is the right hand rule?
Okay, so the right hand rule, I mean, like, how do I explain it? So basically
you have to tell
the
me
index.
What is the finger? Yeah, go on.
So the index finger represents the field. The thumb represents the motion. And 1 second. Yeah, and the fingers. Which finger represents the current, sir? I don't remember that.
The second finger. Second.
Okay,
for current.
the second middle finger. Yeah,
right.
Okay.
Second. C for current. The curve for current. First finger. First for far field. Thumb. M for motion. Thumb.
Yeah. Okay. Got it.
Okay. Now that's the right hand rule. What is the right hand rule used for? Shrey?
It's used to wait 1 second. Calculate motion from like the field and current, I think.
No. You're supposed to find EMF, find basically the current, right? Slash EMF, they're the same thing in this case. They are in the same direction. So find EMF slash current due to motion. That's the right hand rule. Neha, read this out.
Right hand rule is basically finding current or EMF due to motion.
Now write this down, please. I'm not going to revise this again. Right? We have done this in the last 3 classes. So please write this down in your notebook. And tell me when you're done.
Just a second. Am I supposed to draw the hand too? I mean.
No, you just write. You're supposed to write the thumb, motion, write the names and the uses.
Okay. Okay. Where's my notebook? Yeah. Physics, magnetism, right? Yeah.
Yes, magnetism. That's the class.
Magnetism. So right hand rule. Index finger represents the field, right? Yeah, field. Second finger represents middle or represents.
Are you done?
Current.
Right, Shreya, can you hear me? I want you to give Ayan a call.
I did. Okay, I'll do. Okay.
Done?
Yeah, and 1 second. I just have to write that find current to find current or EMF due to motion. Done, sir.
Done. Okay, right hand rule. Fine. Now, just a second. I want you to draw, do another thing. That is, what is the left hand rule?
Okay, so yeah, left hand rule.
Anas, can you hear me?
Yeah.
Write down on your notebook, write down Fleming's left-hand rule. Write down the uses of the fingers. The thumb is the motion. First finger is the field. Second finger is the current. Write this down on your notebook.
All right.
As soon as you're done, tell me.
The left hand rule, the fingers are the same,
The
right?
fingers are the same, yes.
Wait, the internet at my house isn't working properly because it's raining outside.
I
So
see.
it's keep getting.
I see. Can you see the screen?
Yeah.
Take a screenshot.
All right.
Fleming's left-hand rule, right? Neha, have you written it down?
Yes, sir. Yes.
Okay, now one thing, if you don't write notes in classes, then it's the whole thing is a waste of time and effort, right? So you should, moving forwards, write everything down in whatever happens in class. Even if you get the notes, right? But you have to have your own notes. Otherwise, you'll forget. Okay, that's the left-hand rule. So everything is same, but what is the purpose? Why do we use this? To find motion due to current. Is that clear?
Yeah.
Write this down. Tell me when you're done.
Sir, one doubt.
Yeah.
The right hand rule is to find the current or the EMF. So what is the left hand to find the current? Wait, no.
It's written on the board
Find
to find
motion.
motion. Motion due to current. The other way around.
Thank you.
We did this in the third class for magnetism, right? So please have notes. Do not forget things.
Yeah.
As soon as you're done, come on, we'll move on. Anas, have you written this?
Yeah.
Yes, Neha?
Yes, done, sir.
Done. Now, so this is fundamental, right? If you don't remember this, then everything in magnetism goes away. This is fundamental. If that's done, let's move on. Now, in the last class, we looked at some things about inducing EMF, right? How EMF is induced. We saw that EMF, the rate of EMF, or just write this down. Write the topic, write a subheading, and over there you should write inducing EMF due to motion. Write down inducing EMF / current due to motion.
Sir, could you repeat?
I'll repeat. Inducing EMF / current for
Inducing EMF
/ current due to motion.
due to motion. Okay.
Anas, have you written this?
Yeah.
Yeah, okay. Now, the next thing you need to write down is EMF is directly proportional to write this down, this whole thing. What I'm underlining right now.
All right.
And this symbol right here, this symbol means directly proportional.
So is it like that's how you write it?
That's how you write it. You write the symbol whenever you want to say directly proportional. You say this. Anas, do you know what directly proportional means?
No.
No. Directly proportional means if one thing increases, the other will also increase. If one thing decreases, the other will also decrease. Now, let's say, what is proportional right now, Neha? Read this down. Read this out. EMF is directly proportional to
EMF is directly proportional to rate of cutting of magnetic field line.
Okay, so if I want to increase the EMF, what do I have to increase? If I want to increase the EMF, I have to increase the rate of cutting of magnetic field. That's what I have to increase.
Okay.
Is that clear? Now, if I what
Yeah.
if I want to decrease the EMF? What will I have to do then?
Go down.
If I want to decrease the EMF, what will I have to decrease to do that? I'll have to
The current.
decrease the rate, not the current, the rate of cutting of magnetic field. What is directly proportional? EMF and rate of cutting of direct magnetic field. Yeah. So if you want to decrease the EMF, you decrease the rate of cutting of magnetic field. Is that clear? If you have two things with the directly proportional sign in the middle, what this means is that if you want to increase the one on the left, you have to increase the one on the right. If you want to decrease the one on the left, you have to decrease the one on the right. Is that clear?
Okay, yeah.
Fine. Now what this tells us is, this tells us how much EMF you'll get, right? That's what it is telling us. Fine. Fine, okay. Now you will have to watch the recording on this class because I really don't want to revise everything. That will take another class, but I want you to write this down. Now, next thing, write this down on your notebooks right now.
Lens law.
Lenz's law, yes.
Yeah.
Anas, do you remember what Lenz's law is?
No.
No, but we did this in the last class, didn't we?
I don't think I was there.
You were there and you did answer a lot of questions. I did ask you if you understood. You said yes. Now onwards, I want you guys to write everything in your notebook, right? Because we are not revising or repeating things in class every day. Is that clear, Anas?
Yeah.
And everyone else. So write this down ASAP, then we'll start today's class. All right, are you done? Neha, can you hear me?
Yeah, 1 second. This last word. Of course.
The induced EMF. This is EMF.
Oh yeah, that's what I was gonna ask. Is the induced what? Yeah, fine.
Induced EMF
Okay.
will always have such a direction to oppose the change causing it. That is your
Done,
law.
sir.
Okay, done.
Yeah.
Now, what is the meaning of this? What this means is, if you let's say you want such a current, the flow of the current in the coil will always be in such a way to oppose the motion of the magnet. Now, why are we getting an EMF? Because what we were doing was we were moving the magnet in the coil, and what this caused was, just a second. Can you see the magnet moving on the board?
Yep.
Now, if I move it to the right now it's moving to the right. Yeah, it's moving to the right. Therefore,
Yeah.
the field lines, are they cutting the coil?
Yeah, right.
Yes, they are. Now that this guy is moving to the right, the field lines are cutting the coil. So therefore, we know that the EMF is induced, right? That's clear. If the field lines are cutting, that means EMF is induced. But now we have to see what is the direction of the EMF. Is it positive? Is it negative? That's the main question.
Yeah.
Okay.
So okay.
But we can't really say that right now. We can't say that yet. But what we'll try to do is, what we'll see is, okay, right now if I move it to the right, there's a current of, let's say, plus 0.1 amperes. Is that clear? That is a current, yeah? Current is measured in
0.1.
Yeah, 0.1.
Fine. Okay.
Right? You can also draw the diagram on your notebook if you're fast enough. I would prefer that. Now,
Okay.
a rough sketch would be perfect. Now, the next thing which we're doing is, right now, okay, let's forget this for a second. Let's look at this magnet right here. Again, you have a magnet. You have the field lines of the magnet. And now, right now, it's not moving anywhere. It's stationary. If it's stationary, will an EMF be induced?
No.
No, it's zero. The EMF or the current is zero right now. Okay. Now I'm moving it to the right. Let's move the magnet to the right. And if I move it to the
Yes, it
right,
is.
then I'm getting a +1 ampere current. Right?
Okay.
Read this, Neha, on the board.
Magnetic field lines are being by the what?
Being cut.
Magnetic field lines are being
Cut.
being cut by the coil, so EMF is induced.
That's clear?
Yep.
Okay.
So which diagram do we have to draw? Could you just show that?
A coil, a magnet, and an ampere.
Okay, right. Okay.
Right? Okay. Right. You should right now take a screenshot, then note this down later. Take a screenshot of the first one.
No, sir. I'm done with the drawing.
You're done with the drawing. Perfect. Okay. Then if it goes right, then I get +1. And what happens is if I go to the left now, instead of going to the right, I'm now going to the left. What that does is it induces an EMF in the opposite direction. So first I was going to the right, the magnet was being pushed into the coil. Then we had a current of +1 amperes. But now if I take the current, the magnet away, I'm getting -1 amperes. Is that clear?
Yep.
Now read this line.
So,
Yeah.
sir, one question.
Ask me. Yeah.
The direction of the magnet is always left, or like is it? It depends on something.
No, it's always left to right, towards or away from the coil. Okay.
Yeah, like I mean towards. Yeah.
Towards
So
away, left
EMF
or right. Yep.
Yeah. EMF induced is negative if magnet is moved in opposite direction. Yeah.
Right. So if it was positive first, if it goes in the opposite direction, it becomes negative. If it was, let's say, negative first, then in the opposite direction it will become positive. Let's do a question on this.
Okay.
Let's do a question on this. Okay, now before we move on, I want you to see. I want you to read this again. The Lenz's law. The one
Which
in the
one?
orange box. This one.
Okay. An induced current always flows in a direction such that it opposes the change which produced it.
Right, you have written it in your notebook, yes? The induced EMF will always have such a direction to oppose the change causing it. Perfect?
Yep.
Now, what does this really mean? Read this out.
Induced current will try to oppose the magnet from moving in that direction.
Right. So what this really means is, if the magnet is moving in this direction, let's say north south, that's a magnet, and if it's moving to the right, what really trying to do is, if it's going to the right, I want to stop it from going to the right. Yeah, that's what I'm trying to do. Now that's not what I'm trying to do. I am trying to push it to the right.
Why are you stopping it?
I'm not stopping it. Let's see what's happening. What's happening is,
never mind.
I'm pushing it to the right. Okay. I'm pushing it to the right. What is stopping it? The induced EMF is stopping it.
The induced EMF. Sorry, yeah, right.
Yeah, it's causing it to stop moving in that direction. Now, why?
Yeah.
Why is not in your syllabus? You need to know that this happens, and that happening is called Lenz's law. Is that clear?
Okay. Yeah.
Now look at one example right here. Now right here we have two people. Let's forget this guy for a second. Let's remove this. Now this is me, and I'm pushing the magnet to the right. Let's see how it looks.
Right. Okay.
I'm going to the right. Yeah, this is how it's moving. Now, if I want to stop it from going to the right, what will I have to do?
You have to wait. No.
If one person is
There
pushing
should
in
be
one
an
direction,
induced.
right? So what we can do is, let's say we bring a person in the opposite direction,
A
and he's going to
person,
push in the other direction.
Okay.
Now, will the magnet stop?
I guess, yeah, it will.
Because two people are pushing in the opposite direction.
Opposite, yeah.
Now, but we don't really have a person pushing. We have something else pushing in our circuit. Let's say. Now, instead of a person, can I bring a magnet? If this magnet was moving in, let's say, to the right, and then I bring another magnet with the same pole, we know that
it will repel. Right. Yeah. Unlike poles attract, like poles repel.
So if I want to stop it, there's another way. rather
You
than
can
bring a
also get a
stick figure,
magnet
get a magnet
with the same pole.
pole. Exactly.
Yeah.
Now that's one way to make magnet stop moving in that direction. Okay. Now what's really happening in the coil as well is if I move the magnet to the right, then the coil induces a magnetism in such a way that the same pole is on the side of the magnet. Okay, so the coil will now have north pole here and south pole on the opposite direction. This was our coil. Okay, we were moving the magnet to the right. Now if I want to stop the magnet from moving to the right, I will have to stop it. Then I'll have to bring a magnet with the same pole, but instead of a magnet, now we have a coil. This coil has north pole, which repels the magnet, right, to stop it from moving. That's the Lenz's law. Okay, but what happens if I move it to the left? Now, if it's moving in the left, then I'll have to bring south pole here to attract it.
So that it attracts. Yeah.
To stop it moving from going away. If it's going away, we attract it. If it's coming close, we repel it. Make sense?
Repel it. Yep.
Okay, now you have this coil right here. Now we know there's a north pole, there's a south pole, but we have to guess the direction of the current. Okay, direction of the current. Okay, now we have something called the grip rule, right hand grip rule. Can you see this?
Yep.
Right hand grip rule. Now I want you to look at it for a second. Tell me what you say. Just in silence, look at it for 10 seconds. No talking.
Okay.
Done?
Yep. So basically, the guy, whoever it is, he's holding a rod with his right hand with a proper grip, and his thumb finger is going towards the north side. I mean, yeah, pointing towards the north side, and the fingers are facing towards the palm. I can say that, right? So you're on mute.
But Neha, can you hear me?
Yeah.
Or Shrey, Anas, can you hear me?
Yeah.
I hope you guys are listening, right? Now you have the right hand rule. Right hand grip rule. Now this grip is important. It's not the right hand rule, right? It's the right hand grip rule. Is that clear, Neha?
Yep.
Now what you're doing is you're making a grip. Your thumb is the field, and the current is your fingers.
Is the fingers, yeah.
Write this down.
Oh, this thing? Okay, 1 sec.
And this is for a coil. What is this for? A coil. So what you have to write on your notebook, all of you, that right hand grip rule for coil. Then thumb is the field, and fingers are the current. As soon as you're done writing, tell me.
Done, sir.
Done. What have you written?
I have written right hand grip rule for coil. Thumb is the field and fingers are the current.
Right. Okay. Perfect. Anas, done. Take a screenshot if you're not done.
Done.
Okay. Now let's go. Shreya, you should also try taking a screenshot if you don't have a notebook. Okay. Now right now we have this. Okay. Now what we can try to do is, let's forget all of this which is already here. Let's remove this for a second. Okay. Fine. And let's just see that the magnet is moving to the right. Then Neha, what will be induced on the same side of the coil, on the left side of the coil, which field will be induced if the magnet moves to the right?
And North Pole only, because
North.
if it's too close, you have to repel.
Repel.
So,
Not too close if it's towards. If something coming
it,
towards
sorry.
you, you have to repel it. Okay, fine. Now you have north and south. Can you use a grip rule to tell me the current direction?
Okay. One second. The current direction will be away. No, wait.
Towards?
It's towards.
Towards, how does that work? So your thumb is now pointing.
It is pointing the north side, and
The
your fingers are
pointing
pointing your own palm.
towards.
So
They're pointing towards. Okay. If they're pointing towards you like this, therefore, what we realize is the current is like this. Okay. So your current will be like this. Just a second. Like this. So
yeah, like that. And then this one will go up.
is that clear?
Yep.
How is it
Yep.
going? It's going towards. It's coming towards you, like
Yep.
this. Fine.
Right. Yeah.
Okay. So if that's clear, then let's just let's do the whole thing. If it's going downwards first, if it's going, sorry, that's not the correct way. Just a second. How was it first? Like this. Guys, can you see this on the board? Is it working for you?
Yes,
Sir,
sir.
it's I don't think it's going towards you. Wait.
Can you see this right now?
Yeah.
Okay, it's working fine. Now it was lagging a bit for me. Just a second. This is the current direction. So you come from here like this, and it goes towards you. So like this.
Yeah, like that. Yeah.
And therefore, this is the so current always flows from positive to negative, right? Conventional current direction. Current is always positive to negative. So if the current is going like this, then this side where it starts is the positive side. This is the negative side. Is that clear?
Yeah.
Yep.
Fine. Okay. Ask me if you have any doubts. Now let's see what happens if instead I move the magnet to the left. Now which pole will be induced on the same side as the magnet? South. Now what happens to the current then? The current will start flowing in the opposite direction.
Current will move opposite. Yeah.
Your thumb will now point to the left like this.
To this left side, and
Not the left side, sorry, to the right side. North.
I mean
North. And therefore your fingers will now point in the opposite direction, which will be away from you.
Yeah.
Okay, so this is how it will look. Instead of going in that direction, now the current goes like this.
Yeah.
So this side becomes positive now, positive, negative. Therefore, what we realize is moving the magnet in the opposite direction changes the current direction. Yes.
Yeah.
So that proves the Fleming's Lenz's law, not Fleming's, but Lenz's law. What is the Lenz's law? That
the induced EMF will always have a direction to oppose the change causing it.
perfect. That's 2 marks in the exam. 3 marks. Okay. Right. I hope all of that is clear. Then let's just do a Q&A for a second. Question. Now, if the magnet right now, you have a coil and a magnet. If the coil is stationary, if the magnet is stationary, what will happen to the EMF? Will it be zero? Will it be positive, negative? If the magnet is
be
stationary,
zero.
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 If I tell you the magnet is moving to the left, when it's moving to the left, right? Moving to the left. Just a second. Then
Positive?
the EMF is
Sir,
positive.
it will be negative.
It is positive. You can't know if it's positive or negative. The question will tell you.
Oh,
Let's
yeah,
say
right. There's
left
no
is
coil.
positive. Then you have to say what happens to the right. If left is positive,
Then
what is right?
right becomes negative.
Negative.
The opposite. Okay. Now that's all the recap. We're starting the next thing, which is applications of inducing EMF. Now just be ready to write things down. Is that clear?
Yeah.
Okay. Okay, if everyone can hear me, this is applications of inducing EMF. I'm going to start recording again. I'm restarting the meeting. Rejoin all of you.
Okay.
We're studying magnetism. We're studying IGCSE physics, and we're starting magnetism 8, right? And today we're looking at the applications of inducing EMF. We looked at how do we induce EMF? What are the rules about inducing EMF? We have the Lenz's law that every EMF, the direction of the EMF will always be in such a way to oppose the change causing it. We also saw that the EMF is always directly proportional to the rate of cutting of magnetic fields. Right, Neha?
Yes,
Now,
sir.
okay, now right now let's just look at the AC generator. The AC generator uses everything what we have studied. But before we look at that, let's just do a simple question. And I need the answer from Ayan, Anas, Shrey, all of you right now. Ayan,
Yes,
can you
sir.
hear me? Okay, perfect.
Yes, sir.
North, south. You have a wire, but you don't have any power supply connected to this. All
Wait,
you have
north,
is a
south, what?
wire, magnets. You have to tell me.
Oh, those are the two ends of the magnets. Okay.
You have to tell me what is the direction of the induced EMF if the force on this wire is, let's say, upwards, or let's say upwards.
Sir, want to be from the positive to the negative terminal?
Say that again.
Want to be from the positive to the negative terminal?
There are no terminals. There is no battery connected. There's no power supply.
Oh.
Yeah. So we have to guess the direction of the current. Which end of the ammeter will be positive, which will be negative?
Sir, it would be
Uh,
it would be clockwise.
It's motion, okay, motion. Now in this case, I'll tell you that you have to use the Fleming's right-hand rule, right? Neha, tell me what is the Fleming's right-hand rule used for?
Fleming's right-hand rule is used for to find the current or EMF due to the motion.
Now you have motion, you have field. What do you have to find? Current, right? So can you use it?
Yeah, current.
Use it.
Yes. 1 second.
Now, Ayan,
So-
work with me. Do you know the right-hand rule? Yeah. So
Yes, sir.
make the right-hand rule on your hand right now.
Sir, it's to the left.
To the left. I see. Now, can you make a drawing on the board, like such like an annotation, perhaps?
Oh wait, no. 1 second. I guess I
I
got.
want
Sorry,
the current. It could
Okay.
either be like like this, or like this. Those are the two possible ways.
Sorry.
Ayan,
Wait.
right
Current
now we
is
have the field to the right, like this. That's your field, and the motion
Yes, sir.
is upwards.
upwards. Yeah. Sir, isn't it right-hand rule?
Let's say instead of upwards, I'm going to tell you that the motion is towards you. The motion
Sir,
is
isn't it right-hand rule?
right-hand rule. Yes, it is towards. Now try again. If the motion is towards you, like this, and then 90 degrees, obviously, where is the
Sir, then
current?
why is the field towards the right?
It is to the right. Yes.
Okay.
The current is. Anas, tell me.
Upwards.
Upwards. All of you, is that clear?
Yep.
That's I, which is current. So in this case, I will be upwards. So what is the positive? Which terminal is positive and negative? So current is always positive to negative, right?
Wait, sir, so it's clockwise, as I said.
It is clockwise, like this. But you can't get the answer in terms of clockwise, but because in the exam, this is all you will have, a wire.
Yeah, I didn't know whether to say upwards or forwards, so I just went with clockwise.
Yeah, so you have to always give the answer in terms of this section of the wire, this part of the wire, this, right? Forget all of the other stuff
All right, sir.
outside. Okay. Now what we'll do now is look at the AC generator. You have the same thing here. You have North Pole, South Pole. You have the section AB. Can you see the wire AB? The section of the
AB?
coil AB.
Yeah.
A to B.
Yeah.
Can you see that? Okay. Instead of a wire, we have a coil here.
Okay.
Okay. So it has different sections to it. Fine. We have section AB. Now tell me if AB is moving upwards, if the motion is upwards, okay, and the field is to the right, where is the
Okay.
current being induced?
It is away from us.
Away from you. Perfect. So the field current is away. Fine. If the current is away, okay, so the purple line, can you see the purple line right now, which is pointing away?
Yep.
That's your
Yep.
current. Fine. Okay.
And, yeah.
Now CD. Look at CD.
Uh,
If you look at CD, the section of the wire CD, now it's pointing downwards.
mhm.
Okay. So where
And the
is the
field
current
is-
pointing? The field is to
Is
the
the
right.
field to the
To the
right.
right.
Okay. So the current is again away from you. No, wait 1 second. Motion is toward
It is
Towards me.
towards you, towards us. Perfect. Towards all of you. Like, does that make sense?
Sir,
Yeah.
how, sir? 1 second.
How?
So the
Okay.
motion is down.
Okay.
With,
I'm going to give you a trick. All of you, please note this down. The trick or the method. Let's because to make it more catchy, let's call it a trick. Whenever you have any complicated diagram like this, just to take things out. The motion is downwards. Make a vector diagram like this. So motion downwards. And where's the field? Right. Now point your fingers in these two directions of field and motion and tell me where is the current on this simple diagram of this towards. So the current is towards like this. Ayan, is that clear?
Sure.
Neha, is that clear?
yeah.
Towards. Another thing, if it's away, if the motion is away, motion is upwards and the current is away, right? If you just flip the motion while keeping the field constant, the current will obviously also flip, right? If you flip one thing, then current will flip, but if you flip both of the things, then there's no change. What's happening is, if I, let's say, if field stays the same and I flip the motion, if the motion now points upwards, then the current will also flip and point away. Is that clear? So if you flip the motion, the current also flips. Right? Does that thing make sense?
Yeah.
Perfect. Okay. So towards current. Fine. Now what's really happening is a current is being produced. Yeah. Okay. Now you have in an AC generator, you have a few components. Let's look at that first. You have a coil. What is the first thing? Write down on your notebook. Components of an AC generator. Ayan, Neha, all of you, Anas. Try to take a screenshot. Components. The first thing is the coil. Second thing, slip rings. Third thing is ammeter. Is that clear?
Only
Oh,
three.
yeah.
Only these three things. Any doubt?
It's not on the screen for me.
It's not on the screen for you. Okay.
Wait, now
fine.
it is.
Now it is. So have you written, guys, have you written down the components of an AC generator?
Yes.
Now, where are the components? This ring right here is the slip ring. Is that clear?
Yeah.
How many rings do you have? You have 2 rings here. How many do you have? 2.
2.
2. Now there's another thing I forgot to mention. That's the carbon brushes.
Yeah, the brushes.
Can you show
Write
that
this
again?
down. I'll show it again. First, write down carbon brushes. And the use of the carbon brushes is to connect circuit to coil.
Sorry, 1 second.
Yeah, done.
The use of the slip rings is to let's say to connect, let's say, coil with carbon brushes. Now write this again. Okay, Neha, just read it from the top once.
Yeah. Components of AC generator: coil, slip rings to connect coil with carbon brushes, ammeter, carbon brushes to connect the circuit to slip rings.
Right. So what's happening is you have an interchange happening here. You have a slip ring, you have the carbon brushes. Now the slip ring is connecting the coil with the carbon brushes. On the other hand, the carbon brush is connecting it to the slip rings. They're just connecting each other. They won't really ask you this in the exam, but you need to know where they are. Okay. The carbon brush is with the circuit. The slip ring is with the coil. Fine. Okay. Now what's happening is, ask me.
It's not
Yes.
related, but it's tuition. Like, do you guys also teach like economics, business, and stuff like that?
Yes.
Okay.
Okay, afterwards. Okay, now you have motion upwards. Now what's happening is if the current is pointing, let's say the purple one, the current right now is going like this. Yes. Look at the purple arrows. The current at AB is pointing away. The current at CD is pointing towards. So is this the motion of the current? The direction of the current, sorry, not the motion, the direction.
Yep.
This is how it is. C to D and A to B. So A to B, then C to D. That's your current. So what's really happening is that this terminal right here, the blue, let's say the blue slip ring, is the positive terminal because that is connected to the AB section. Now the green one is the one which is connected to the CD part, which makes this terminal of the ammeter negative and this one positive. Is that clear? This is positive, this is negative. So where the current is starting, it's positive. Where the current ends up, that's negative. Clear? Now what's really happening is that the coil is actually rotating. It's not just like that, it's actually rotating. Now we are doing the motion. Okay, we're rotating the coil. Now what really happens is when I rotate this right here is the new section of the coil. Can you see the new one? Which is rotated 90 degrees. The blue highlighted section is the coil rotated 90 degrees. Can you see this? Yes, no?
Yeah.
Yes, you can.
Yes, sir.
Good. Okay, if you can see that, then now what's happening is the current, the motion is now pointing to the, which direction is the motion? The blue arrow. It's to the right. Yes? If the motion is to the right, let's find the current direction again. Motion is to the right. Okay. Where is the field? What is the field direction? Ayan, where is the field direction? How do you find the field direction? North
Yeah,
to
I'm
south?
working it out.
It's always
it
north
should be
to
north to
south,
south. Yeah.
right? Because we only have magnets. Only magnets have the field. So the magnet north, it's always north to south. So again, it's to the right. The field is also to the right. Okay. Now the thing is, if field and the motion both are to the right, motion and the field, then we can't use the right hand rule, can we? Because the whole point of right hand rule is that they're 90 degrees to each other. Neha, in the right hand rule, are the fingers 90 degree to each other? Yes, no.
Sir, could you repeat?
Yes, can you hear me? Now, what I'm asking is, in the right hand rule, is any finger in the same direction?
No.
No. So if, for example, in real life, we have field and motion in the same direction, then can you use the right hand rule?
No.
Because you can't point both the thumb and the finger to the same direction. That's not possible. So therefore, if they are not perpendicular, if motion and field are in the same direction, then the current becomes zero. What does it become?
Sir?
The current is now zero.
Zero.
Because
Yeah. Because
why is it?
this
Because they're in the same direction.
direction. Yeah.
Okay. Now let's look at this. Let's look at angle wise. The first Ayan, read this 0 degrees.
Sir, sorry to interrupt.
Degrees.
Yeah.
Actually, sir, there are only 5 minutes left. I have to. Actually, I have a festival going at my home, and my grandparents are calling me. So could I go?
Can you stay for five minutes? We'll just
Okay,
finish
I'll try to.
0 to 90
Yeah.
degrees. This part, and we'll look at DC motors afterwards. Ayan, if you look at this, you
Right.
have 0 degrees. This is actually pretty important, right?
Yeah.
0 degrees. Now, right now, what's happening is the AB section is connected to the first slip ring right here. Okay, the top one, and CD is connected to the down one. Can you see that? So the AB section of the wire, we had AB section of the coil right here, AB. That one is connected to the lower slip ring. Yes, and the CD section
Yeah.
is connected to the green ring. Is that clear? You have the blue
Yes,
ring
sir.
and the green
Yes,
ring.
sir.
Fine. Now, in the first section, the AB section of the wire was moving upwards, and the CD section was moving downwards. The field was to the right. The field is always to the right because we're not changing it. Fine. The motion is upwards, down at AB, so we get positive side at the AB section and negative terminal at the CD section. So this slip ring right here becomes negative. That's what we saw. And this right here becomes positive. Is that clear? Because the current is starting here and going like this. Current is starting here and going to the CD section. Is that clear?
Yeah.
Yes, sir.
Fine. Just a second. Now what happens if I move the whole coil 90 degrees? If I move it 90 degrees, now from here, AB was here, it goes from here to here. 90 degrees, right? 90 degrees. If it moves 90 degrees, now the motion is towards the right, and the motion at CD is towards the left. The whole coil is being rotated clockwise, like this. The field did not change, but what we realize is the induced current now becomes zero because the motion is parallel to field. They're in the same direction. Okay. If motion is ever parallel to field, the current is zero. Neha, read this out.
Yeah.
0 amp meters because